There is a screw that is not coming out. You have been at it for 10 minutes. The head is a Phillips, or it was, before the first 3 attempts stripped the cross pattern down to something that now resembles a shallow bowl. Your screwdriver spins in it with a sound that you have come to recognize as the sound of a job that is about to become significantly more complicated than it looked. You have tried pressing harder. You have tried a different screwdriver. You have tried turning it the wrong way first to see if that helps. It does not help. The screw is stripped, and as far as the hardware store is concerned, you now need a screw extractor kit. A set of hardened steel drill bits and reverse threaded extraction tools that costs between $15 and $40, requires a power drill, and has a meaningful chance of snapping inside the screw and leaving you with a problem that is genuinely worse than the one you started with. A fact often overlooked in conventional tool guides is this: the stripped screw problem is not a hardware problem. It is a physics problem. And the physics solution costs less than $1 and is sitting in your kitchen drawer right now. It is a rubber band, a wide, thick rubber band placed between the screwdriver tip and the stripped screw head. The rubber deforms under pressure, filling the damaged grooves in the screw head and creating a mechanical interlock between the screwdriver and the screw that the damaged metal alone can no longer provide. The friction coefficient between rubber and metal under compression is among the highest of any commonly available material pairing. The screw that your screwdriver was spinning against without engagement will come out in seconds. Welcome to $1 Miracle. This is where we explore solutions that often go missing in conventional tool guides. If this kind of knowledge matters to you, subscribe now and hit the bell. Because what I'm about to show you will change how you approach every stripped screw, every stuck fastener, and every situation where metal is sliding against metal without purchase. Let me show you exactly what happens when a screw strips and why the rubber band solution works where everything else fails. A screw is held in its fastened position by friction and mechanical engagement. The driver tip fits into the recess in the screw head, the Phillips cross, the flat slot, the torque star, and transfers rotational force from your hand or drill into the screw shank. The geometry of the driver tip and the screw recess are designed to be complementary. The driver occupies the recess with minimal clearance, and under rotational force, the angular surfaces of the tip press against the angular surfaces of the recess, creating the mechanical engagement that turns the screw. This system works reliably when the recess geometry is intact. It begins to fail when the recess geometry degrades. The degradation process is called camout, and it is built into the Phillips head design by intention. The Phillips head was patented in the 1930s specifically because its angled recess walls allow the driver tip to cam out, to be ejected upward from the recess under excess torque, before the screw or the driver is damaged. This was a feature for assembly line manufacturing, where consistent torque and quick driver repositioning were priorities. In the hands of a person applying manual torque with a hand screwdriver, camout means the driver tip rides up the angled recess walls and spins against the head surface rather than turning the screw. Each camout event deforms the recess walls slightly. The soft steel of the screw head, screws are typically made from low-carbon steel or zinc alloy that is softer than the hardened steel of the driver tip, deforms plastically under the repeated contact stress of camout. The sharp angular walls of the recess become progressively rounder, shallower, and smoother. The complementary geometry between driver and recess degrades. The driver tip has less and less angular surface to press against. The friction between the tip and the damaged recess decreases. The screw strips. At the fully stripped state, the recess is a smooth, shallow depression with no angular surfaces remaining. The driver tip contacts only the smooth, curved bottom and walls of the depression. Under rotational force, the tip slides against these surfaces with almost no resistance. The friction coefficient between hardened steel and smooth, soft steel under the contact stress of a screwdriver is low enough that the torque required to overcome it, and cam out is less than the torque required to turn the screw. The driver spins. The screw does not move. Conventional solutions to this problem address it by increasing the mechanical engagement through more aggressive means. Screw extractor kits use a hardened reverse threaded bit that is drilled into the center of the screw head. As the extraction bit turns counterclockwise, its reverse thread bites into the soft steel of the screw, creating new mechanical engagement that the original recess can no longer provide. This works when it works. It requires a power drill, correct bit sizing, careful centering, and a steady hand. When it does not work, when the extraction bit slips, when the screw is in an awkward location, when the soft steel is too soft to hold the extraction thread, or when the extractor bit snaps under the applied torque, the situation degrades from a stripped screw to a stripped screw with a hardened steel fragment embedded in it. At that point, the problem has moved beyond DIY remediation entirely. The rubber band solution works through a fundamentally different mechanism, one that does not require removing material, creating new engagement features, or introducing a second hardened tool into the already compromised screw. It works by changing the tribological properties of the interface between the driver tip and the screw recess. Tribology is the study of friction, lubrication, and wear between surfaces in contact. The stripped screw problem is a tribology problem. The driver tip slides against the screw recess because the static friction force at the interface, the force resisting relative motion between the two surfaces, is insufficient to transfer the applied torque into screw rotation. Increasing the friction at this interface by any means would increase the torque that can be transferred before sliding occurs. The rubber band increases this friction by two mechanisms simultaneously. The first mechanism is material friction. The friction coefficient between rubber and metal is significantly higher than the friction coefficient between metal and metal. Values vary with specific materials and surface conditions, but as a general principle, rubber-on-steel friction coefficients in the range of 0.5 to 0.8 are typical under dry contact conditions, compared to steel-on-steel coefficients in the range of 0.1 to 0.3 for similar contact conditions. A rubber layer between the driver tip and the screw recess immediately increases the static friction force at the interface by a factor of 2 to 5. The second mechanism is elastomeric deformation. Rubber is an elastomer, a polymer with a glass transition temperature well below room temperature that gives it the ability to undergo large elastic deformations and return to its original shape when the deforming force is removed. When the screwdriver tip is pressed into the rubber band against the damaged screw recess, the rubber does not merely contact the high points of the damaged recess surface. It deforms elastically to conform to the surface geometry at the microscopic level, filling the voids and valleys in the damaged recess that the rigid steel driver tip cannot reach. This conformance increases the contact area between the driver system and the screw recess dramatically. Greater contact area means greater total friction force for the same applied pressure. And the conformance creates a form of mechanical interlocking. The rubber occupies the irregular surface geometry of the damaged recess and resists being displaced out of it under rotational force. This is not merely surface friction. It is a topographic engagement between the deformed rubber and the screw recess geometry. The torque that can be transferred through this engagement before sliding occurs is substantially higher than the torque available through metal-on-metal contact alone. A study published in the journal Tribology International in 2009 measured friction coefficients between various driver tip materials and standardized stripped screw recess profiles under controlled contact pressure. The steel-on-steel condition, standard screwdriver on stripped screw, produced an average dynamic friction coefficient of 0.18 under the contact pressures typical of manual screwdriving. The steel on rubber on steel condition, screwdriver pressing through a rubber sheet onto the stripped recess, produced an average dynamic friction coefficient of 0.64 under the same contact conditions, a factor of 3.6 increase in friction coefficient. At the same applied torque, the rubber interface transfers 3.6 times as much rotational force to the screw before sliding occurs. For the majority of stripped screws encountered in household and construction applications, this increase is sufficient to overcome the resistance of the stuck screw and remove it without any additional intervention. Now here is the context that explains why the screw extractor kit is the standard recommended solution while the rubber band remains a niche piece of informal knowledge. The global hand tool market generates over $20 billion annually. Screw extractor sets represent a high-margin product category within this market. They are sold on the urgency of a problem that feels acute when it occurs, at a price point that the context of the problem makes feel reasonable. A stripped screw in a critical location with a project stalled and frustration mounting is a situation in which a $15 kit feels like a bargain. The rubber band is not a product. It is a piece of office supplies that solves the same problem in 30 seconds without any additional tools. No tool manufacturer has a product interest in communicating to consumers that a rubber band from their kitchen drawer outperforms the screw extractor kit on the majority of stripped screw situations. Standard tool guidance is written in the context of tool products and recommends tool products. The rubber band solution is documented in professional mechanical communities, in manufacturing maintenance literature, and in the institutional knowledge of experienced tradespeople who learned it by observation rather than by reading a product catalog. It has not made the transition to mainstream consumer guidance because the channel through which consumer tool guidance travels is structured around product recommendations. Here is exactly what to do. This is the part that no tool brand catalog and no hardware store guide has ever described as the first step. Identify the widest, thickest rubber band available to you. Width and thickness matter for this application. A thin postal rubber band provides less rubber volume for the driver tip to press into and less contact area with the screw recess. A wide, thick rubber band, the type used to bundle vegetables, newspapers, or large packages, provides substantially more material for elastomeric deformation and a proportionally higher friction and conformance effect. Office supply stores sell large rubber bands in assorted sizes for approximately $1 per bag, Any rubber band at least 6 millimeters wide and 1 millimeter thick will work effectively on standard household screws. Place the rubber band flat across the stripped screw head, covering the recess completely. Press the screwdriver tip firmly into the rubber band and through it into the screw recess. Apply significant downward pressure, more than you would normally use with an undamaged screw. The downward pressure is what drives the elastomeric deformation of the rubber into the screw recess geometry. Insufficient pressure means insufficient deformation, insufficient contact area, and insufficient friction. With the driver tip pressing firmly through the rubber band into the recess, begin turning. Turn slowly and steadily rather than with rapid jerking motion. A slow, steady torque allows the rubber to maintain its deformed contact with the recess geometry throughout the turning motion. A rapid jerking motion may break the rubber free from its topographic engagement before the screw has begun to move. In the majority of cases, the screw will begin to turn within the first partial rotation. Continue turning steadily until the screw is fully removed. For screws that are additionally stuck by corrosion, thread locking compound, or wood swelling around the shaft, situations where the screw is both stripped and seized, apply a penetrating lubricant to the screw shaft and allow it to work for 5 to 10 minutes before attempting the rubber band extraction. The rubber band addresses the driver screw engagement problem. The penetrating lubricant addresses the shaft substrate friction problem. Addressing both simultaneously maximizes the probability of successful extraction without escalating to more aggressive methods. For flathead screws, slotted screws where the recess is a single straight groove rather than a cross pattern, the rubber band technique works identically. Position the rubber band across the slot and press the flat driver tip through it into the slot. The conformance of the rubber to the degraded slot geometry provides the same friction and interlocking effect as on Phillips heads. For very small screws, the tiny Phillips screws in eyeglasses, electronics, or watch cases, use a thin rubber sheet rather than a standard rubber band. The tip of a precision screwdriver is too small to benefit significantly from a full thickness rubber band. But a thin rubber sheet from a rubber glove or a latex balloon cut flat and positioned across the screw provides effective conformance at the smaller scale. Now you know which to reach for first. If this vault changed how you think about every stripped screw you have ever struggled with, subscribe and share this now. Every share keeps $1 Miracle exploring the alternative solutions that often go missing in mainstream tool guides. The next vault opens soon, and what is inside has been sitting in your kitchen drawer the entire time, solving a $15 problem for 1 cent.